Welcome to the Deep Dive. Today, we're getting into the really complex relationship between Earth's climate, its huge oceans, and, well, the clouds hanging over us. This deep dive is really for you if you're someone keen on understanding complex stuff, properly, but also fairly quickly.
Exactly. And we've got some fascinating sources to work with today. There's a scientific paper looking at Earth's climate history, some great info from NASA on climate change, mitigation, adaptation, the works, and also a pretty interesting problem-solving activity. It sets up a scenario linking global warming, wind speed, ocean activity, and cloud formation. It includes some diagrams, student sheets, things I'll refer back to kind of illustrate how these systems connect.
Okay, right. So let's unpack this. Our mission today is basically to pull out the key insights from all this. We want to understand how rising global temperatures might kick off the sort of chain reaction affecting winds, stirring up the oceans, changing the clouds, and ultimately what that all means for the planet's temperature. We're looking for those aha moments.
Definitely. Let's kick things off with the scenario in that problem-solving activity. It basically suggests that if Earth's temperature goes up significantly, because of an enhanced greenhouse effect, so more heat-trapping gases warming the planet, then we should probably expect global wind speeds to increase.
Right. That makes intuitive sense, doesn't it? More energy in the system, things move faster. And this connects directly to what NASA says in their mitigation and adaptation information. They stress that even if we stopped all greenhouse gas emissions right now, the warming and climate changes already baked in would, keep affecting future generations.
Yes, and what's really striking is that emissions are still going up. NASA points out a pretty big milestone. Back in 2013, the daily CO2 level in the atmosphere went past 400 parts per million, for the first time in human history, that is.
Wow. And that scientific paper on climate history really puts that number into perspective. It tells us levels like that haven't been seen for, 3 to 5 million years back in the Pliocene. That kind of long view really highlights just how significant things are right now.
So building on that scenario again, the next step in this proposed chain is that these faster winds will cause more disturbance in the ocean water, greater turbulence, more mixing. You can sort of picture stronger winds making bigger waves, churning up the surface more.
Okay, so the wind stirs up the ocean, and the scenario says this disturbance can then lead to larger clouds forming. It seems like a leap from choppy water to clouds way up high.
Well, yes, but there is a mechanism. The analyzing a feedback loop diagram in that activity gives us a key piece. It suggests higher winds mean bigger waves, and these bigger waves actually release more tiny salt particles into the air. These act as sort of seeds, condensation nuclei, for water vapor to grab onto and form cloud droplets.
Ah, okay. Salt particles. Right. So the ocean literally seeds the clouds above it, especially when it's rougher. But here's the kicker, isn't it? The clouds themselves then affect temperature. The scenario asks, how could bigger clouds make Earth warmer? And how could they make it cooler? It's clearly not straightforward.
Not at all. If we look at student sheet 2, it explains the potential cooling effect. If you get thicker clouds or just more cloud cover overall, they could act like a giant mirror, bouncing more sunlight back into space before it even reaches the surface. That would limit warming. It's a potential negative feedback, basically trying to stabilize things.
Okay, so a natural break, potentially. That sounds, hopeful, but the scenario also says clouds might increase the temperature. How does that work?
It really boils down to the type of cloud and how high up it is. That same student sheet 2 makes a crucial distinction. Thick, low clouds are really good at blocking sun, but thin, high, wispy clouds, cirrus clouds, they're not so good at blocking sunlight coming in. And worse, they can be quite effective at trapping heat radiating up from the Earth like a thin blanket, so they can actually contribute to warming. It depends entirely on what kind of clouds form more often.
Right, so it's not just more clouds, it's which clouds and where. That really complicates the outcome, doesn't it?
It really does. And speaking of complications, student sheet 2 brings up another really important feedback loop: ocean warming itself. We know the oceans absorb a huge amount of CO2 from the atmosphere. They act as a massive sink.
Yeah, they do us a big favor, basically mopping up some of our excess CO2.
They do, but here's the catch. As atmospheric CO2 increases, the atmosphere warms, and that warming eventually heats up the oceans too. Now, the critical point is that warmer water can hold less dissolved gas, including CO2. It's just basic chemistry. So as the oceans warm, their ability to absorb CO2 from the atmosphere actually decreases.
Oh, so you get this cycle. More CO2 warms things up. Warmer oceans take up less CO2, which leaves more CO2 in the atmosphere, which warms things up even more.
Precisely. That's a potential positive feedback loop. The system that's helping to buffer the change becomes less effective because of the change. It can amplify the initial warming.
That does sound concerning. A cycle that could accelerate warming.
It is, and that's why the work NASA does, outlined in mitigation and adaptation, is so vital. They provide the hard data we need to track and understand these things. Think about missions like GRACE and GRACE-FO, measuring ice sheet changes down to the millimeter, or the Sentinel-6 and JASON satellites tracking sea level rise so accurately.
Right, they're like the planet's doctors, taking its vital signs, giving us the objective data.
Exactly, and NASA is very clear their job isn't to make policy, it's to provide that robust scientific data to everyone, the public, policymakers, scientists around the world, so informed decisions can be made.
And all of this circles back to the really fundamental Earth systems, like the carbon cycle mentioned in the carbon cycle source.
That's right. You have the fast cycle carbon moving between, say, plants, the air, the oceans relatively quickly, and the slow cycle involving rocks and geology over millions of years. But the key point for us today is that human activities, mainly burning fossil fuels and changing land use, are pumping extra carbon gases into the atmosphere via that fast cycle. And that disrupts the Earth's energy balance, leading to warmer temperatures.
And we're seeing the real-world results of that warming in things like sea level rise. That's covered in the State of the Science fact sheet, sea level rise, and coastal flooding.
Yes, and that fact sheet lays out some stark numbers. Globally, sea level has already risen about 6 to 8 inches in the century, from 1920 to 2020, and crucially, the rate of rise is speeding up. Along the U.S. coast, it's actually been more like 10 to 12 inches on average over that same period. This is happening for two main reasons. Melting glaciers and ice sheets adding water, and the water itself expanding as it gets warmer, thermal expansion.
Wow, 10 to 12 inches already along the U.S. coast. And the acceleration is key. What does it project going forward?
Well, the projection highlighted is that along U.S. coasts, we're likely looking at another 10 to 12 inches of relative sea level rise just in the next 30 years, so between 2020 and 2050. Think about that. The same amount of rise that happened over the previous 100 years is projected to happen in just 30. It really underscores that acceleration.
That's quite something. So let's bring it back to the scenario in these feedback loops. The problem-solving activity, define them clearly, right? Negative feedback tries to dampen a change, maintain balance. Positive feedback amplifies a change, pushes things further away from the original state.
Correct. And it's worth remembering, like you said, positive doesn't mean good here, and negative doesn't mean bad. It's just about whether the effect reinforces or counteracts the initial change in the context of climate.
Right. Okay, so let's try and synthesize all this. The big question in that conference scenario, this whole chain reaction warming, winds, oceans, stirring bigger clouds, will it ultimately increase global warming, positive feedback, or decrease it, negative feedback?
Well, based on everything we've looked at, particularly Student Sheet 2, the answer is it's really complex and uncertain. It genuinely depends on those cloud characteristics. If the result is significantly more low, thick clouds.
The sunblock clouds.
Exactly, the sunblock clouds. Then that could exert a cooling influence, a negative feedback, counteracting some of the warming.
Oh,
But if the change leads to more high, thin cirrus clouds, they could trap more heat, acting as a positive feedback, making things warmer. And remember, the initial warming itself drives more evaporation, potentially leading to more clouds generally, which could be seen as a negative feedback starting point. But Student Sheet 2 is very explicit about the uncertainty. We don't know for sure what types of clouds will increase or where latitude matters or even when they'll form more. It's a huge area of active research.
So the cloud effect is a major wild card in the whole climate equation. Its net effect, positive or negative, is still pretty up in the air, so to speak.
Very much so. And then you layer on top of that the other feedback we discussed, the ocean warming one, where warmer oceans take up less CO2. That one seems more clearly like a positive feedback, likely amplifying warming. So you've got multiple feedback loops interacting, some potentially counteracting warming, others potentially reinforcing it.
Okay, so wrapping up this deep dive then, we've seen how global warming might ramp up wind speeds, churn the oceans more, and lead to bigger clouds. That part seems plausible. But the crunch point, whether those clouds ultimately cool or warm the planet, is really tricky. It depends heavily on the cloud details, introducing major uncertainty. We also looked at that worrying positive feedback where warming oceans absorb less CO2, potentially making the problem worse. And the reality check of sea level rise shows us these changes aren't just theoretical, they're happening and accelerating.
Exactly. Hopefully, walking through these sources has given you, our listener, a better handle on just how interconnected and complex Earth's climate system is. Maybe a few aha moments along the way about those connections.
Absolutely. Which leads us to a final thought for you to mull over. Given this delicate balance, these competing feedbacks, and the clear changes already underway, what do you think are the most crucial unknowns? Where should scientists really focus future research and observation to get a better grip on the long-term consequences for our very dynamic planet? Something to consider as we all keep learning. Thanks for joining us for this deep dive.